Section 4.1 and 4.2 solve the non-homogeneous second order problem of this form. And it's going to sound very much like what we did in section 1.8, where we solved the first order non-homogeneous equation. In other words, throw away the second derivative here, and that's basically what we solved in section 1.8. And you remember there that the general solution was the general solution of the homogeneous equation plus any particular solution. And the general solution of the homogeneous equation has the, well, it had one arbitrary constant. Now it's going to have two arbitrary constants because second order. But the thing is, if you plug this into the equation, the homogeneous part plugged into the left-hand side gives you 0. The particular solution gives you F, so 0 plus F is F, so it's a solution. But you've got, it's not sufficient to just have a particular solution. You need the general solution because you're normally going to have initial conditions, so you need the arbitrary constants in there. And that's the arbitrary constants will be in here. So the general solution with two arbitrary constants will be the general solution of the homogeneous equation, which has the two arbitrary constants plus the particular solution. Well, in section 3.6, we learned how to solve the homogeneous equation. So this part, so there's two parts to solving this equation. There's finding the homogeneous solution, which we'll talk about first, which we talked about in section 3.6. And then there's the finding the particular solution, which is going to be very similar to what we did in section 1.8. Just have a second order equation here now, but same rules for what to try. So section 3.8, we went through how to solve the homogeneous equation. That's the first part of solving the non-homogeneous equation. And, well, you try solutions of the form e to the pt, and you get a quadratic equation, mp squared plus bp plus k equals 0. And there's three possibilities. If the discriminant of the quadratic equation is positive, you've got two distinct real roots, so your general solution is just a linear combination of two solutions, e to the pt and e to the qt, where p and q are the two real roots. They're irrational, that's fine, but they have to be real. Then if their discriminant is negative, so you've got two complex conjugate roots of the form alpha plus or minus beta I, then we found that the homogeneous solution has the form a e to the alpha t cosine beta t plus b e to the alpha t sine beta t. So your two solutions now are e to the real part t cosine of imaginary part and e to the real part t sine of imaginary part. And the third possibility is if the discriminant is 0, there's only one real root, then e to the pt, of course, is one solution, but the other is t e to the pt. And by the way, that's only a solution when p is a real root. If there are two roots, then t e to the pt is not a solution, so it's there for you when you need it and only when you need it. So this was section 3.6. Then, like I said, it kind of belongs in chapter 4 because it's the preliminary to sections 4.1 and 4.2. So you have to find the homogeneous solution. For section 1.8, it was a first order homogeneous equation, and that was always separable, so it was real easy to solve. This one's harder. The homogeneous problem's a little harder. And in fact, in 1.8, the constants, these didn't even have to be constant because it's still separable, although the rules for what to try for the non-homogeneous part only work when they're constant, so they kind of do need to be constant. Okay, so that's the first half. Section 3.6, we've been talking about that. Solve the homogeneous equation depending on what the roots of your characteristic equation are. Now, independent of that, or almost independent of that, is the second part. That's find the homogeneous, the non-homogeneous solution. And the rules are basically the same as they were back in section 1.8. The fact that the left-hand side is second order is not really important. What you try is still given by those rules. Basically, if the right-hand side, the f, is an exponential, you try an exponential of the same frequency. In other words, these are just examples here, of course. I thought we had enough constants running around. I didn't want to put a variable up there. So it's obvious what I mean here. If it's 3e to the 8t, you try alpha e to the 8t. If it's 3e to the minus 4t, you try alpha e to the minus 4t, obviously. So if the right-hand side is an exponential e to the something t, you try e to the something t times alpha, and you plug it in, and you try to see what alpha needs to be to make that work. If the right-hand side is a cosine or a sine or both, and in this example I've assumed that its frequency is 3, but of course that can be anything. So if it's something times cosine of 3t or something times sine of 3t or both, regardless, you have to try the whole thing, alpha sine of 3t plus beta cosine of 3t. Don't just try cosine if it's a cosine. You got to try sine and a cosine. Same rules as in section 1.8. If the right-hand side is a polynomial of degree 3, you try a full polynomial of degree 3. Even if there are terms missing, like the t squared terms missing here, you still have to try full alpha t cubed plus beta t squared plus gamma t plus delta. So if the right-hand side is an exponential, a sine or cosine, or a polynomial, we know what to try, and the rules are the same. By the way, these rules only work if the left-hand side, they're constant coefficients, so if they're not, then you've got a problem. It still is true that if you can find a particular solution, general solution is still general solution of the homogeneous equation plus particular solution. It's just almost impossible to find a particular solution if they're not constant, so we'll assume they are, same as in section 1.8. If the right-hand side is not an exponential or a sine or a cosine or a polynomial, you're pretty much out of luck. And furthermore, remember that sometimes these things they say to try don't work because, for example, if a solution of the homogeneous equation is e to the 8t, then this obviously won't work because you plug it in the left-hand side, you get 0. If cosine of 3t or sine of 3t are solutions of the homogeneous equation, that won't work. So the rule is, if the first 3 rules don't work, multiply by t and try again. So these are basically the same rules as in section 1.8 of what to try for a particular solution. And once you find a particular solution, you're not done because you want the general solution, so you have to add the general solution of the homogeneous equation, which is one of these 3 depending on what the roots of this characteristic polynomial are. Okay, a very interesting application here. This is the spring problem with B equals 0, so we took mass to be 1, K is the spring constant, and there's no friction, so B is 0. We're going to ignore friction. And the right-hand side is like an external forcing function, cosine of omega t. You can imagine that there's some kind of a magnetic field that's applying a force to the metal weight in the spring, or maybe it's a wind, it's oscillating wind, but there's some external force. So the forces acting on this are the force of friction, which we're taking to be 0, the force of the spring minus ky, and an external force, cosine of omega t. So that first we solve the homogeneous equation. The characteristic equation is lambda squared plus k. The roots are plus or minus square root of ki. So the real part, so there's 2 complex conjugates. The real part is 0. E to the alpha t is e to the 0t. And then, so the general solution of the homogeneous equation is just cosine of square root of kt, sine of square root of kt. The e to the alpha t is just 1. So there's the homogeneous part. That's a type 2 homogeneous equation there. Now the particular solution. Well, we said the right-hand side cosine omega t. You try alpha sine omega t plus beta cosine of omega t. Plug that in to the differential equation. Take the second derivative of this. There it is. You get power of omega for each derivative and a minus after 2 derivatives. Then plus k times y. There's y. That has to be cosine of omega t. Get the sine of omega t's together, and you got k minus omega squared alpha. But that's supposed to be the coefficient of sine of omega t, which is 0, so alpha is 0. Get the cosines together, and you got k beta minus omega squared beta cosine omega t equals 1 cosine omega t. So beta times k minus omega squared is 1. So beta is 1 over k minus omega squared. So and alpha is 0, so our particular solution is 0 plus 1 over k minus omega squared cosine omega t. So there's our particular solution, there's our general solution, and the initial conditions determine what A and B are, but we're not too interested in those. This is the solution. Now the interesting part here is what happens when omega is very close to square root of k. Then this denominator becomes 0, almost 0. So if the frequency of the applied external force is close to the square root of the spring constant, then you've got a resonance effect where you have a really large solution. This will be a huge, almost infinite amplitude. And that can actually happen if you have a structure that has a certain spring constant and you apply that force to it. It'll resonate with it and basically break the spring. Now, what if omega is exactly equal to the square root of k? Then, if omega is exactly equal to the square root of k, that means you're getting exact resonance. Then cosine of omega t and sine of omega t are actually solutions of the homogeneous equation. So it couldn't possibly work to try solutions of that form, because you plug in the left-hand side, you get 0. And see, that's what happens. This becomes infinite, and this is no longer valid. So what do? Well, the rule 4 says if rules 1 through 3 don't work, multiply by t. So we multiply the thing we're trying the whole thing through by t and plug that in. And it takes a little more work because you have to use the product rule and so forth, but plug that in and set the whole thing equal to cosine of omega t. End up with beta equals 0. This time alpha equals 1 over 2 omega. So your particular solution then is, that's alpha is 1 over 2 omega, and that's 0. So it's t over 2 omega times sine of omega t, and then there's the homogeneous solution. And notice this increases, the amplitude increases with time, so it's resonating, all right, it's blowing up. With time, the amplitude of the spring gets bigger and bigger. Of course, it won't really, it'll break at some point or hit the roof, but in theory, it keeps increasing the strength forever. So that's resonance. Now, in a real problem, your friction will not be exactly 0. B won't be quite 0. So you can't ever get this exact resonance, but you can get close to it. Then if B is small and omega is close to the square root of k, you'll still get a large coefficient there. So you still get near resonance. And in fact, in the book it talks about the RLC circuits. That's an electronic circuit with a resistor, capacitor, and an inductance coil. And the equations for the RLC circuit are exactly like the spring, damped spring equation, just different constants mean different things. And if you apply an external voltage like a radio signal, then you can get exactly this kind of resonance, and that's basically what makes radios and TVs work. For a given constants for the circuit, R, L, and C, there's a certain resonant frequency. And if your externally applied radio signal has the resonant frequency, you'll get a large response, and you won't if it doesn't. So that circuit will only tune in to a particular frequency. Well, that's assuming R is 0. R is the resistance is equivalent to the frictional coefficient here. If it won't ever be exactly 0, but you try to make R as small as possible, so it'll behave like this. If R is small, then you adjust the capacitor and the inductance coil until it fits the frequency of the radio signal you want, and you'll get resonance there. And the smaller R is, the bigger the resonance will be. In theory, it could be infinite if the resistance is 0, but of course it won't ever be exactly. In fact, I'm old enough to remember old transistor radios. You could open them up and you could actually see a capacitor, and when you turn the dial, it changed the capacitor. You could see it basically changing the coefficient of the capacitor, which changed the frequency, and so you could pick up a different radio signal. I'm sure they're not that simple to understand now. The DE Tools has a forced mass spring app that let's look at. And let's take off the amplitude of the right hand side to be 1. So it's solving this problem here. We're going to take B to be 0. So just try to solve the equation we just showed you. So there's no friction. And I'm going to take K to be 2. M is 1. Then the resonant frequency will be the square root of K, or square root of 2. So if I set the external frequency, see the F is 1, it doesn't matter much. M is 1, K is 2, so the resonant frequency is the square root of 2. And if I try some other value, let's say something that's not the resonant frequency, and start the spring going. Well, it's not calculating it very accurately, is it? But it's not going off to infinity. It's there's no damping, so it doesn't die off either, but it's not going off to infinity. Now, if I change the frequency to the square root of 2, let's see how close I can get that to 1.41. We'll take 1.42, that's approximately the square root. So we're close to resonance now. Let's see what happens when you pull the spring back. So there's no friction. K is 2, so the resonant frequency is square root of 2, and I'm applying external force with frequency square root of K. And let's see what happens now. Well, the spring goes back and forth, but the vibration gets bigger and bigger because that factor T, the amplitude is proportional to T, and it's going to eventually break or something.